All right, it's time to start getting into displacements. We have spent time looking at forces, and now we're going to calculate the displacements associated with those forces, starting with statically determinate trusses. By the end of this lecture, you should understand the relationship between the energy caused by external loadings and the resulting internal strain energy. And we can use the principle of virtual work to determine the deflection in a truss subjected to external forces. Now, I'm going to do a little bit of theory. We're going to do some derivations to get to the virtual work approach. So please just stay with me and we'll get through it, and then we'll move on to actually applying the principles that we are discussing. So we're going to calculate deflections using energy methods, and we're going to use something called the conservation of energy. Right? Makes sense. We want to conserve energy. We don't want to lose energy. So conservation of momentum, all of those wonderful things that we talked about back in physics class, we're going to apply them to doing virtual work. So conservation of energy means, and I'm going to use the letter U for my energy. That's a terrible U. UE is equal to UI. That means the energy expended by the work done by external forces and moments, right? Work and energy are interchangeable. Work is a type of energy, right? Work done by external forces and moments is equal to the internal work due to the strain energy. Okay, so the work associated with external forces or moments is equal to the internal energy, the strain energy of the deformations, right? The energy it takes to deform, right? So I'm going to focus on forces first because we're talking about trusses. And trusses only have axial loads in them, if you recall. So let's say I have this rod and I apply a force gradually. I apply a force F. And as I apply that force, the bar starts to displace a small amount dx. So I apply force F causing displacement dx. Displacement. And I can write an equation the change in external work done by that force to displace that dx is equal to that force times that displacement. Right? You might remember from physics, work is force times displacement. So my change in work is equal to my force times the change in displacement. Now I'm going to gradually apply apply force F and my displacement is my total displacement I'm going to assume that my total displacement, right, let's say assume total displacement x has a linear relationship, right? This is like if it's a spring and you slowly increase the weight that you're applying, right? Apply a tiny little weight to your spring, measure the displacement. Apply another tiny little weight, measure the displacement. And it's always linear related, right, with that spring constant. It's the same thing that we're talking about here. I'm going to look at it on a graph, right? If my force is on the y-axis and my displacement is on the x-axis. My total displacement. And let's say I apply all the way up to, I incrementally apply all the way up to a load P apply a force equal to P, causing total displacement delta. Right? There's my delta, my P. So I can write my force equation related to X as P over delta, that's the slope, right? P over delta times X. I guess you could also say at some point you apply a load P, causing delta. So I'm going to look back at this equation up here, my change in external work, and I'm going to replace that F with P over delta times X dx. And we're going to integrate, and we're going to integrate from X equals 0. That's I have 0 total displacement, all the way up to X equals delta. And I see that my external load, or my work done by that external load is 1/2 P times delta. It's also, right, it's the area under this curve is what I'm doing. One half base times height, or height times base, right? P times delta. So my external, the work done by that external force to apply a total of delta displacement is equal to 1/2 P, my final force, times that displacement delta. Previously, you probably would have seen that, I just don't like, that looks prettier. And now my D looks funny too. That's better. Previously in physics, right, we had work equals force times distance, but that is if you instantaneously apply a force and it deflects and it moves something delta. Now we're gradually applying it, so there's that 1/2 in front of it. So that is the equation for the external work done by a force to cause a displacement. It's that area under that curve. Now I'm going to look at the internal forces. What's going on, right? That force what's going on inside my bar here? The external work translates to internal strain energy. And I know that I have to have conservation of energy, so my external work is going to equal to my internal strain energy. And let's say that P, that force that I applied, is causing an internal load of N, an internal axial load. And the axial load doesn't vary along the length, so I don't have to do any additional math here. It's going to be constant along the length. And my bar has a length of L and an area of A. And this internal axial load is causing a deflection, baby delta. Now I just figured out that if I apply a force gradually up to P, causing a total displacement delta, that the external energy is equal to 1/2 P times big delta. So if P and N, right, so if I'm doing the same thing, applying an axial load, N causing delta, then that work associated with that load is equal to 1/2. I'm going to replace that P with the internal load N, and that big delta with my baby delta. Now I want to get an internal strain energy. I'm going to relate that to the stresses and the strains that are caused by this internal axial force and this displacement, right? So that internal axial force, axial load, is causing a stress, which is equal to N over A, right? My force over my area. And that deflection is causing a strain equal to the deflection over my length, my original length. And if I have a linear elastic material, I know I can relate stress and strain by my elastic modulus. Right? Hooke's law. So let's set the stress due to the force and the stress due to the strain equal to each other, and substitute that strain equation in there. So I have stress is equal to N over A, which is also equal to E times my strain, delta over L. If I solve for that delta, I get NL over AE, which might seem kind of familiar, right? Deflection due to an axial load, PL over AE, NL over AE, right? N is just the normal force, the internal force. If I substitute this into here, I get an equation for my internal strain energy of 1/2 N squared L over A E. So the work done by the external force that deflected it is 1/2 P times big delta, the deflection that external load is causing, and I can find the internal energy by looking at the internal forces on the bar times the length over the area and the elastic modulus, the material and geometric properties. Right now, N and P are equal to each other because all I have is one bar with one load on it. All right. So let's remember these two equations. All right. The work done by external load P to cause a deflection delta is equal to 1/2 the internal axial forces that load causes times the length over the area times the elastic modulus. Give a little summary. I have my work of my external load. UE is equal to 1/2 P delta. And that is equal to the work of my strain energy, 1/2 N squared L over AE. If I did a graph of the total displacement times the applied force, and I took the area under the relationship between those two, I would get the work caused by external loads to displace the structure. And similarly, if I applied an internal load causing a deflection delta, and I took the area under that curve, I would get the internal strain energy. Right, that's where we get our 1/2 n times delta, baby delta. And the area under these two curves, I hope they look different enough, should be equal to each other. Gonna stop right there. That's how we first developed the conservation. Well, yeah. That's how we first developed the conservation of strain energy, or conservation of energy.